Okay, in this video I'd like to do an example of FM radio and the sampling theorem. And so what I'll do is I'll start by saying that FM radio has a signal bandwidth of about 15 kilohertz, and therefore when we listen to the FM radio we have audio signal frequencies that are going from 0 to 15 kilohertz. Okay, so let's assume that that's our audio signal and that we're going to digitize this audio signal. Okay, and so the first question is for part A, if we sample this signal at a frequency of 20 kilohertz, that is a sampling rate of 20 kilohertz, is this sufficient? And the answer there is no, because the Nyquist frequency is twice the highest frequency. And so our Nyquist frequency, Fn, is 2 times 15 kilohertz, or 30 kilohertz. Okay? And so, in order to successfully sample an FM radio signal that occupies from 0 to 15 kilohertz, we would have to sample that signal at 30 kilohertz. And so 20 kilohertz is not sufficient. Okay, so for part B, I will sketch the spectrum if the signal is sampled at 20. Well, let's sample it correctly at 30 kilohertz first. Okay, and in this case, what we're going to see, let's see, I'm going to go make a sketch like the ones in the notes, and I'm going to go ahead and plot frequency versus power, starting at 0 frequency, and I'm going to go ahead and go 5, 10, 15, 20, 25, 30. So here's 15, and here's 30, 35, 40, 45 kilohertz. Okay, and if my signal occupies the range from 0 to 15, I'm going to go ahead and draw my signal to look like this. So let's suppose that we could draw anything here. We could draw any kind of squiggly line we like for our signal to occupy that 0 to 15. But drawing this triangle helps us keep track of an inverted spectrum versus a non-inverted spectrum. So if we sample this at 30 kilohertz, then 30 kilohertz sort of becomes our new 0, in exactly the same way that last week we did frequency division multiplexing, and we had up-converted a signal, and the mixing frequency became the quote new 0, and I had copies of the signal to the left of it which were inverted and to the right which were not inverted. And so this signal that we get looks like this. It has its power in the range from 0 to 15, but then if I sample it at 30 kilohertz, I also have another copy from between 30 and 45 kilohertz and an inverted copy between 15 and 30 kilohertz. And in fact, I can go ahead and draw this out every 30, 45, 60, 75, 90, 105, etc. in the frequency. Okay, so that's what the spectrum looks like if we sample it at 30 kilohertz. And you can see that that's why we need to have the Nyquist frequency at twice the highest frequency in the signal. That keeps this inverted copy from overlapping the original signal. So part C, let's see what happens. Let's sketch the spectrum if the signal was sampled at 25 kilohertz instead. And you're going to see here that when we do this carefully, we're going to get a big problem with fold-over distortion. Okay, so I'm going to do power versus frequency again. 5, 10, 15. Can you see it? There we go. 20, 25, 30 kilohertz. I like to label that. 35, 40, 45 kilohertz, etc. Okay, so my original signal is again in the range from 0 to 15. And now I'm going to go ahead and sample at 25 kilohertz, and that puts a new copy of the signal centered at 25 kilohertz. So the non-inverted copy of the signal goes from 25, 15 above 25 is up to 40. Okay, 30, 35, 40. But the inverted copy goes 15 below 25. 25 down to 20, 15, and 10. Okay, so here you see now that we have a big problem with fold-over distortion. The normal thing you do after sampling a signal at, for example, 30 kilohertz is low-pass filter it to keep only the part of the signal that you're going to keep when you do your digital to analog. So once we've digitized this signal and we want to go back to analog, we're going to low-pass filter it, as I showed in my slides, from 0 to 15, and hopefully that recovers our entire signal because that's the bandwidth of the signal. But here, when we do our low-pass filtering from 0 to 15, we're going to get some extra copies of the fold-over distortion contained in that signal. And so, for example, the frequency at, let's see, we have 0, 5, 10, 15. If I go to the frequency 1 is 14 kilohertz. That frequency being 1 away from the end, 1 away from 15, let's draw it right here on this spectrum. It's 1 away, 1 back from 15. That frequency is going to appear 1 away from 10 in the inverted frequency spectrum, or right here. So the frequency F1 of 14 kilohertz appears as 10, 11 in the fold-over distortion. Okay, and that I hope helps with one of your homework problems where it does give you a situation like this, which is called undersampling. We haven't sampled it fast enough. We've sampled it at less than the Nyquist frequency, and with undersampling we do get fold-over distortion, and one of your homework problems asks you to do the same thing. So here again I just used the symmetry of the problem to calculate that 11 kilohertz from the picture. Hope that helps on your homework. Thanks.